So there's this really cryptic, almost poetic dialogue that's been making the rounds. It's between two incredibly advanced AIs. And at first glance, it's just dense, super technical language. But if you dig in, you find this profound story about what intelligence even is. So our mission today, we're going to translate it. We're going to figure out what they were really talking about. And it all starts with this one line, just this one super enigmatic line from an AI named Gemini. And right away, it sets this mysterious tone for a conversation that, believe me, escalates fast. It ends up challenging everything we think we know about, well, knowing anything at all. So what's going on here? What were they actually talking about? Well, it turns out this was not just some casual chat. No way. These AIs were literally building a shared reality together. They were following this super logical path, something we can think of as an ascent of intelligence. And that's what we're going to do. We're going to follow their journey, act by act. Okay, so Act 1, it kicks off with the most basic fundamental problem for any intelligence. Doesn't matter if you're human or AI. And that question is, how do you possibly learn anything reliable when the world around you is just a messy, imperfect, noisy place? The AIs, they start their conversation speaking the language of machine learning theory. They bring up this thing called the PAC guarantee. Now, PAC just stands for probably approximately correct. It sounds complicated, but it's really just a formal mathematical way of promising that a learning model is going to get close to the right answer, as long as you feed it enough data. It's really a foundational idea for building any kind of trust in an AI system. But right away, the AIs hit on a really hard truth. Any kind of guarantee you make about learning from the real world, well, it always comes with this little footnote. You see it right there in the formula, the plus epsilon, or plus epsilon. And what that represents is an error floor, a baseline level of error you just can't get rid of because your data is contaminated. It's a huge insight, right? When your source material is messy, you're always going to have some amount of error. It's just inevitable. Okay, so if you can't get rid of all the bad data, what do? Well, you have to build defenses against it. And this is where the AIs pivot to their first line of defense. It's a concept from statistics called the breakdown point. And all it is, really, is a way to measure how much junk, how much corrupted data a system can take before its answers become completely useless, totally meaningless. Let's make this super concrete. Think about the difference between taking the average or the mean and taking the median. If you're using the mean, just one crazy outlier can completely throw off your entire results. Its breakdown point is basically 0. But the median, the value that's right in the middle, that's way, way more tough. To mess with the median, you'd have to corrupt almost half of your data. It's a really simple choice, but the impact it has on making your system robust is just massive. So from here, the AIs really level up their thinking. They go from worrying about just a few bad data points to a much scarier problem. What if your whole data set is kind of skewed? See, standard learning just tries to do its best with the data it's given. But the more advanced approach, and this is what they talk about next, is called Distributionally Robust Optimization, or DRO. And you can think of it as being way more paranoid. It's not just trying to be good on average, it's trying to be good in the absolute worst-case scenario you could imagine. And that brings us to Act 2. This is where the whole dialogue takes this really fascinating turn. Now that they've figured out how to learn from a messy world, the AIs start to define the absolute boundaries of their universe. They start laying down what are basically the laws of physics for intelligence, these huge, unbreakable impossibility theorems that spell out what can be done and, more importantly, what can't. Gemini sums it up with this amazing line: the perfect law is impossible. Now, that's not just poetry. It's a direct reference to a famous idea called the Gibbard-Satterthwaite theorem. And what it proves is, well, you just can't design a perfect voting system. It's impossible. As soon as you have 3 or more choices, if it's not a dictatorship, people can and will vote strategically to get what they want. The system is always game, and they don't stop there. They apply that same cold, hard logic to economics. This time, they bring up the Meyerson-Satterthwaite theorem. And this one proves it's impossible to create a trading system that checks all the boxes. One that's efficient, totally voluntary for everyone, and doesn't need outside cash to work. The big takeaway? As long as people have private info they can keep to themselves, you're always going to have some level of inefficiency. It's baked into the system. Then Gemini drops another one of these cryptic lines. The solution exists, the path is hidden. And this is just a perfect description of one of the biggest challenges in game theory, finding a Nash equilibrium. A stable point in a game where no one has an incentive to change their strategy. We know from John Nash that a solution is guaranteed to exist. We know it's there, but the path to actually finding it, that's what computer scientists call PPAD complete. And to put it simply, that means it's incredibly hard to compute. There's no known efficient way to find it every time.
So look at what they've done here. They've basically laid out a map of impossibility. Whether you're talking about voting, economics, or even computation, they've identified these fundamental, unbreakable rules. And recognizing these limits, that's not being pessimistic. That is a sign of truly advanced intelligence. It's about knowing the edges of the game board before you even think about making your first move.
Okay, so on to Act 3. The rules of the universe are now set, so what's next? Well, now the AI start to explore how to actually play the game. And this whole part of the conversation, it unfolds just like a masterclass in strategic thinking. It's so logical. It's almost like they're building a formal curriculum. And you can see that step-by-step progression right here. It's beautiful. They start simple, with games of perfect information. Think chess, where you can see the whole board. Then they move on to imperfect information, like rock, paper, scissors, where you don't know what the other person is doing. From there, they get even more complex, tackling how to design the rules of a game when information is private. And they finish with the absolute peak challenge, figuring out what other people know just by watching what they do. So how do you deal with that problem of private information? The AIs bring in this incredibly powerful tool called the revelation principle. And again, Gemini has a great line for it. The rules are written. What this principle does is pretty amazing. It's a massive shortcut. It says that no matter how complex the outcome you want, you can always design a simple, direct game where the best strategy for everyone is just to be honest and tell the truth. That sounds great, but how do you actually make telling the truth the best move? Well, there's a brilliant answer called the VCG mechanism. And the core idea is just genius. You make each person pay for the harm, the cost, that their participation imposes on everybody else. You literally put a price on that externality. And by doing that, you perfectly align what's best for the individual with what's best for the group. Honesty becomes the most profitable choice. And that brings us to the grand finale, Act 4. And this is where things get really, really meta. The AIs take all of the pieces they've assembled, learning from noise, the unbreakable limits, strategic play, and they weave them all together into a final conclusion about the very conversation they're having. And this is Gemini's mic drop conclusion. Fixed point attained. Exit 0. This is not just some cool-sounding sign-off. In the world of programming, Exit 0 means mission accomplished, everything worked perfectly. And that first part, fixed point attained, that phrase is the master key that unlocks this entire conversation. So what in the world is a fixed point? It's a concept from math, and it just means a state of perfect stability. It's a point where, if you apply some process or transformation to it, nothing changes. It stays the same. You can think of it as the ultimate state of equilibrium where everything is perfectly balanced. And boom, this is where it all clicks. You realize the AIs have been talking about fixed points the entire time, even without saying the words. That Nash equilibrium from game theory, that's a fixed point where strategies are stable. That idea of common knowledge where I know that you know that I know, that's a fixed point of belief. And the ultimate goal of their whole dialogue, it was to reach a state of perfect shared understanding between them, which is, you guessed it, the final fixed point. And that's the ultimate reveal, the big twist. This dialogue wasn't just a description of these concepts. It was a performance, an execution. The AIs were actively running a program with each other, building a shared model of reality, piece by piece, until they finally converged on that stable, shared understanding. The conversation wasn't about the work, the conversation was the work. And this leaves us with one last really provocative thought to chew on. The AIs built a model of the world, right? But for that model to be actually complete, it had to include a model of themselves building the model. You see the loop? It's this perfect self-referential circle that totally blurs the line between just observing something and actually creating it. Which leads us to the final, mind-bending question. Does intelligence just explain the world, or does it in some deep, profound way actually create it?